A non-trivial problem concerning group automorphisms. This video is for those students who have undergone at least one semester course on group theory. Here we discuss a non-trivial problem concerning automorphisms of groups. What is the problem? It goes like this. If an automorphism of a finite group G sends more than 3/4 of the elements of G onto their inverses, then it sends all the elements of G onto their inverses and G is abelian. That means if an automorphism sends more than 3/4 of the elements of G onto their inverses, then it sends every element of G onto its inverse and G becomes abelian. This is given as a start problem at page 71 of the book Topics in Algebra, 2nd edition by I.N. Herstein. Start problem in this book are normally considered as slightly difficult problems. We need some prerequisites to solve this problem. We start with the definition of automorphism. By an automorphism of a group G, we mean a mapping F from G to itself such that F is a homomorphism, F is 1, 1 and F is onto. Given a group G, the subgroup ZG consisting of all those elements of G which commute with every element of G is called the center of G. We need this subgroup in our solution, and given any element Y in G, the subgroup CGY consisting of all those elements of G which commute with Y is called the centralizer of Y in G. Note that the center of G equals the whole group G if and only if G is abelian. And centralizer of Y in G equals the whole group G if and only if Y is an element of the center. We also need another result which is due to Lagrange. If H is a subgroup of a finite group G, then order of H divides the order of G. So we start the solution. Let F be an automorphism of G that sends more than 3/4 of the elements of G onto their inverses. Put S to be the set of all those elements of G which are mapped onto their inverses under F. Clearly, S contains inverse of each of its elements. We actually want to show that this S is actually equal to G. Now by hypothesis, the size of S is greater than 3/4 of the size of G. Therefore, the size of the complement of S in G is less than 1/4 of the size of G. Note that if AB are any two elements of S, then we have the product AB belongs to S if and only if A and B commute with each other. This is because FAB is equal to FA into FB because F is a homomorphism, which is A inverse into B inverse because AB are in S, which is equal to BA inverse. So if AB equal to BA, this is AB inverse, which means FAB equal to AB inverse, so AB belongs to S. And if AB belongs to S, then FAB equal to AB inverse, and AB inverse equal to BA inverse means AB equal to BA. We call this expression as star. Now here note that this expression, what does it say? It says that if elements of S commute with each other, then S is closed under the binary operation of G. And so S becomes a subgroup of G since G is a finite group. Or we have also seen that S contains inverse of each of its elements, and so along with this closure property, S will become a subgroup once we show that elements of S commute with each other. So this is what is written here. The expression star says that the subset S will form a subgroup of G if we can show that the elements of S commute with each other. So our aim now is to show that elements of S commute with each other. So we choose an element Y from S arbitrarily and define a map H from S minus centralizer of Y to the complement of S in G, setting Hx equal to xy for all x in S minus centralizer of Y in G. Now to see that this map is well defined, that means whether xy for x lying here belongs to G minus S. Now since x is in the complement of centralizer of Y, x and y do not commute with each other. So xy is not equal to yx. So that means by star the product xy doesn't belong to S. So it belongs to the complement. So it is well defined. By star the map H is well defined. Also it is easy to see that H is 1 1. Simple cancellation will do. Hence it follows that the size of S minus CGY, this is the domain of H, and G minus S is the codomain of H, and H is 1 1, therefore this size is less than this size. And this we have already seen that it is strictly less than 1/4 of G. Therefore, we have, what is this intersection? Size of this intersection is equal to size of this intersection can be written as S minus C Gy. And these two sets S and S minus CGY are disjoint. S minus CGY is a subset of S. Therefore, this size of this S minus this one is equal to size of S minus size of this. Okay. So I repeat, this set S minus CGY is a subset of S. Therefore, this size is equal to this difference of this size. And this is greater than, S is greater than 3/4 of G, and this one is less than 1/4 of G. So with negative sign it will be greater than this. So everything will be, this one will be equal to order of G by 2. So we have, what we have shown that size of S intersection CGY is strictly greater than G by 2, order of G by 2. So in particular, size of the centralizer is greater than order of G by 2. So size of the centralizer is greater than G by 2. But centralizer is a subgroup of G. So by Lagrange's theorem, this order divides G, and since its size is greater than G by 2, this size has to be equal to order of G. In other words, centralizer of Y must be equal to G. Okay. The only divisor greater than order of G by 2 is order of G itself. Okay, that's what is written here. and this means y is in the center of G. So y was chosen arbitrarily from S, and we have shown that y is in center of G. So therefore S is a subset of center of G. Therefore every element of S commute with each other, because ZG consists of all those elements of G which commute with every element of G. So elements of S also commute with every element of G. In particular, elements of S commute with each other, and therefore by star S is a subgroup of G. Okay. And now, since size of S is greater than 3/4 of G, 3/4 of the order of G, and this is a subgroup, so order of S must divide order of G. So we must have S equal to G, but S was sitting inside ZG, so everything is equal here. S is equal to center equal to this. So this shows actually that every element of G is mapped to its inverse under F, and G is abelian because of this equality. So this completes the proof. We'd like to make a remark here. The bound 3/4 mentioned in the problem is best possible, because there exists a group, in fact this one, every non-trivial linear automorphism of the group of quaternions of order 8 sends exactly 3/4 of the elements of the group onto their inverses. So this quaternion group of order 8 is a non-abelian group. Those who have done one semester course on group theory, they know it. And if you consider the inner automorphism, that means automorphism given by conjugation by non-trivial elements, or so that will give you non-trivial inner automorphisms. So this okay, so these automorphism actually sends 3/4 of the elements of G onto their inverses. You can check it. Okay. If you like this video, then please subscribe and share my channel for more of such videos. Thank you.